Welcome to the second video in a series on modular form, and this video will be a continuation of the discussion on the construction of elliptic functions. So I remind you, an elliptic function is a meromorphic function that is doubly periodic, and we wanted the periods of this function to be omega 1, omega 2, such that they have non-real ratio. So the ratio of these we want it to be not real. And what we did in the last video is that we managed to prove that functions that take the form the sum over omega of 1 over z minus omega to the alpha is actually an elliptic function whenever alpha is strictly bigger than 2. And just as a quick recap, I remind you that to prove this, we needed the fact that this sum of 1 over omega to the alpha, as alpha ranges over the lattice generated by omega 1, omega 2, is absolutely convergent precisely when alpha is strictly bigger than 2. And we managed to use Weierstrass test to prove that the tail of the series z minus omega to the alpha, whenever omega is bigger than a certain number r, so we fix r positive, and we prove that the tail of this series is absolutely uniformly convergent on the disk of radius r. So after we did that, we had an absolutely convergent tail of the series. So the remaining terms were these things to the alpha for omega less than r. And these things are finitely many because a meromorphic function has finite number of periods in compact subsets of the plane. And thus this thing has poles of order alpha at every period, but these are finitely many, and thus the whole series is actually a meromorphic function. And since it's absolutely convergent, we managed to prove periodicity by a rearrangement argument. So last time we could find elliptic functions of order alpha for alpha strictly bigger than 2. So we could find elliptic functions of order 3, 4, etc. However, we failed to find an elliptic function of order 2. So to complement the work of last time, we're gonna try to construct an elliptic function of order 2, because this is the thing we're gonna need for our first construction of modular forms. So this is a quick recap of what we did last time. So now we turn to the construction of an elliptic function of order 2, which we shall call the Weierstrass P-function. So the Weierstrass P-function is defined as 1 over z squared, and we sum over 1 over z minus omega squared. However, to guarantee absolute convergence, we have to add a correcting term to this. That is 1 over omega squared. We're gonna claim that P is actually an elliptic function, but before we prove this, so let us motivate why we need this correcting term. So recall, to prove that the elliptic functions of alpha are elliptic of order alpha, we had to use absolute convergence for rearrangement argument, because we wanted to say that f of z plus omega 1, which is the sum over 1 over z minus omega 1 to the alpha, we had to say that this is the same as f of z by a rearrangement argument, because as omega runs over all the element of the lattice, so does omega minus omega 1, but we'll be summing the sum in a different way. So we needed some sort of independence of rearrangement, and this was guaranteed by absolute convergence. So this correcting term is added to guarantee the absolute convergence of this series. And you can think of this function as the antiderivative of the function f3. So let me just elaborate on what I mean here. So the function f of z equal to the sum of 1 over z minus omega cubed. This is an elliptic function of order 3, and if we take the antiderivative of this, so if we look at the tail of this series, which we know is absolutely uniformly convergent, and we take the antiderivative of this, by the local uniform convergence of this tail, we can interchange these, sum and integral, and the antiderivative of this thing inside is just takes the form 1 over z minus omega squared minus 1 over omega squared. And having done so, we'll be getting the Weierstrass P-function that we have. So what we're gonna do now is that we're gonna try to prove that the Weierstrass P-function is an elliptic function of order 2 by trying to prove that the tail of this series is absolutely uniformly convergent, and the rest of the terms will just be poles of order 2, and this will give us a meromorphic function. And due to absolute convergence, we will manage to prove that series is actually periodic with periods omega 1 and omega 2. So the next theorem we're about to prove is that P is an elliptic function, and it's also an even function. So we're gonna head to the proof, but before that, let me just remind you that the reason we're interested in this function is that when we consider the Laurent expansion of this function, which we're gonna do after this proof, we will get modular forms of even weights as coefficients of this function. So let us prove this theorem now. So the first step in the proof is to prove the absolute convergence of the tail. So this will be easy because I remind you last time what we could do is that we managed to prove that z minus omega to the alpha is bounded by c over some constant over omega to the alpha. And this thing we proved for every alpha. So particularly if we take alpha equals 2, so if we take alpha equals 2, we have this inequality. However, this thing is just, if we expand it, it's gonna be just something of the form z times 2 omega minus z over something like omega squared times z minus omega squared. And I remind you that we're interested in local in local absolute uniform convergence. So we're gonna consider some disk, right? We're gonna consider some disk, and then we're gonna consider those omegas that are that have modulus bigger than that r. Because we're gonna sum, just as we did for the case of general alpha strictly bigger than 2 over here, we considered the sum for the omegas that are outside the disk. We're gonna do the same here for the case of alpha equals 2. So again, this thing will lose to by this inequality, and this inequality. It's easy to prove that this is bounded by 3 CR over omega cubed, and this is very nice because we know that the sum 1 over omega to the alpha is absolutely convergent for alpha strictly bigger than 2, and we just have here an order 3 here. So we actually have absolute uniform convergence by Weierstrass test. So since again, just to restate this, so since this sum is convergent, then the sum over these terms strictly bigger than r, because we've restricted to the omegas that are strictly bigger than r, is actually convergent, and it's moreover uniform, right? It's a uniform convergence by the Weierstrass test. So this proves that the tail of the series we're interested in, which is the sum of 1 over z minus omega squared minus 1 over omega squared, if we range over the omegas that are not 0, can be written as the sum over the omegas that are strictly bigger than r plus the sum over the omegas that are less than or equal to r. Now this this term is an absolutely uniformly convergent series for for z less than or equal to r, so it's a local thing, and this thing have finitely many terms that takes this form, and thus it has finitely many poles of order 2 at every period, but these are finitely many, and thus we get a meromorphic function. And not only do we get a meromorphic function, we also get absolute convergence of the tail, which allows us to do rearrangements as we wish. So it's possible to do some quick rearrangement of the series and prove periodicity now, but we do a slightly different thing. So let us go back to the proof. So far we proved that the function that we have is meromorphic, and it's locally absolutely convergent. So we now have to prove that it's periodic to wrap up the proof of the fact that it's elliptic. So I remind you that we proved that P is actually the antiderivative of series of the form 1 over z minus omega cubed. So if we take the derivative of that function, we should get back what we started with, right? And we know from the previous video that this function over here is elliptic. And in particular, it's actually periodic with periods omega 1 and omega 2. What does that mean? And should this imply that the function itself is periodic? Well, of course, because if the derivative is periodic, then p prime of z plus omega 1 is equal to p prime of z, right? Because the derivative is periodic. Now, the difference of these will be a function whose derivative is 0, and thus if we integrate that function, we should get something like p of z plus omega 1 minus p of z is actually equal to some constant. And the only thing that we have to do now is prove that this constant is 0, because if we manage to prove this, then the function will, like p at z plus omega 1, will take the value p at z, and it'll be periodic. However, for that, we need a fact about this p function, which is that it is even. So let me tell you how is this helpful before we prove that it is actually even. So if we manage to prove that p minus z is actually equal to p at z, what do we get? We get the following. So let us do this trick of plugging z equals minus omega 1 over 2 in this equation, and what we get is p at omega 1 over 2 minus p at minus omega 1 over 2 is equal to the constant. And since p is even, what we get is that this thing is equal to this thing, and hence the constant is 0, and thus the function is periodic. So the only thing that is left to be proven is that the function is even. So let us see how we can see this real quick. Now, if you plug minus z in here, if you plug minus z in this equation, this thing doesn't change. This thing doesn't change, it's independent of z, and we're left with this thing, right? So this thing will take the form of minus z minus omega squared of z, and this is just 1 over z minus omega squared if we change the sign inside the square. And what do we get? We get minus omega. We get the same form, except that we're getting minus omega over here. And since omega runs over all the elements of the lattice, so does minus omega due to the symmetry in the lattice. And thus, this sum will be the same as p of z by absolute convergence of the series, or by the absolute convergence of the tail of the series. So this wraps up the proof of this theorem that p is actually an elliptic function, and it's also an even function. So the next thing we're going to do is that we're going to consider the Laurent expansion of this series, and this should give us our first construction of modular forms. So let's see the Laurent expansion of the series. So here's a theorem that we're going to prove right now. If we take the Laurent expansion of p of z, it's going to be something of the form 2n plus 1 times some term, which will turn out to be a modular form of even weight, times z to the 2n. So this thing that we're defining over here, g of tn, if we're summing over all the omegas that are non-zero, so these are the omegas that are in the lattice but except for 0, and these things are our first candidates of modular forms and are in fact modular forms of even weights. So we're gonna talk about this in the coming video, but for now let us complete the proof of this theorem, and in the coming video we're gonna talk about the reason as to why these are actually modular forms. We're gonna prove that the Laurent expansion of P of z takes this form. However, there's a little technicality that we need here. So this is not true for every z, but we need to do some technicality here. So if we have to introduce, so let the number r be the minimum of the moduli of the omegas that are in the lattice, which we know is generated by two periods. And what we're gonna do is that we're gonna consider the z's that are positive and less than r. And the need for this requirement will be clear in the proof. But before that, let me justify why this number r is actually positive. Why is this r positive number? Well, it is positive because otherwise the function will have arbitrarily small periods, and a function having arbitrarily small periods is actually a constant. So to see this, suppose that the function had arbitrarily small omegas, right, that are periods, then we can take a sequence of these that are converging to 0, and what we do is that we look at the derivative of the function. In this case, it's the p function. So if we look at the derivative of this at a z, this is gonna be the limit as n tends to infinity of f of z plus omega n minus f of z over omega n. However, f of z plus omega n is actually equal to f of z because omega n is a period for every n, and thus the derivative would be 0. And this will be the case for every z, and hence the function is a constant, which is not true actually. The function is not a constant. So this number actually exists and is positive. So let us now do the proof for this theorem. So we're gonna start by considering the p function that we have. So the p function that we have actually takes the form, let me just rewrite it for you here. So p of z is equal to 1 over z squared plus the sum over the omegas that are non-zero of 1 over z minus omega squared minus 1 over omega squared. So this is the function that we have, and we want to consider the Laurent expansion of this function. So we'd better study what this summand is. So we can easily find this because this term, which is 1 over z minus omega squared, we can rewrite it as so let me just justify the equality here. So this this thing, which is z minus omega squared, can be rewritten as 1 over omega squared. If we take omega squared out, this is going to be 1 minus z over omega squared, right? And it's actually an elementary fact that this will be 1 over omega squared times the sum of 1 plus the sum over n plus 1 of z over omega to the n, as n goes from 1 to infinity. Let me just justify this here. So this thing is the case because just a derivative of a geometric series. So recall the geometric series 1 over z is equal to the sum over z to the n as n goes from 0 to infinity. This is for z less than 1. And if you take a derivative of this, you should get this form in here. But there is a little one thing that we have to justify, which is that why is it that this thing is less than 1? So this justifies the technicality that we needed in the statement of the theorem. So we introduced this number R that is the minimum over all the moduli of the periods. So we have that this R is less than or equal the modulus of any period, right? And the other thing that we have is that we have that Z is between R and 0. And thus, if we consider Z over omega, this will be less than 1. So this is the term that we get if we expand this, and we get this summation over here. Okay, and now that we've gotten this identity, we can just like subtract 1 over omega squared and substitute back in the definition of P of Z, and we get that P of Z is actually equal to this sum. Now, what we'd like to do is that we'd like to bring these omegas inside, right? We'd like to bring these omegas inside so that we get the g of Tn we're looking for, because we want to have ultimately a sum over n over a g of the two n's. So to do that, we will have to switch the summations. But why can we do that? Well, the reason we can do that is that if you look at this sum, which is this thing, in absolute value, right, this is just equal to, so this is a minus and this will be an equal, this will just be equal to this in absolute value. And thus, since we know that the tail of the series is absolutely convergent, we have by dominated convergence theorem that switching the sums is okay. So we can switch the sums, and once we switch the sums, we're gonna get something like the sum over n equals 1 to infinity of the sum over omegas that are non-zero, and then we're gonna have something like n plus 1 here, and then we're gonna have 1 over omega to the n plus 2, and then we're gonna have z to the 2n. We're gonna have z to the n. So there is a little thing that we have to notice before we wrap up the proof of the theorem, which is that the function p of z was proven to be even, which means all the odd terms in this Laurent expansion will vanish, and we know thus that g of 2n plus 1 is 0 for every n. And this will prove this identity here. This will prove that this equality, this is g of n plus 2, right? So this will prove that g of z is actually equal to n plus 1 times g of 2n, because the odd terms vanish, z to the 2n. So this completes the proof of the Laurent expansion of P of z. And we're gonna wrap up this video by saying that that these things that we got will be proven to be modular forms of even weight, and this will be the topic of the next video.